Hello everyone and welcome back. So this time we're talking about potential energy. Now potential energy is a measure of the amount of work a conservative force will do when a body changes position. Remember, conservative force, I don't care about its acceleration or its velocity. That's got nothing to do with the work I'm doing. So in general, for a conservative force system, we can define a potential function. And it's usually a function of position. It's going to be taking into account a lot of things like gravity or springs. And when we do that, we're going to have to figure out how to calculate their magnitudes. Because depending on where we defined our position from, it's going to change things. Like for example, potential energy due to gravity. You are going to have to specify a datum for these problems because your position is going to be from that datum. And your potential energy, or gravitational potential energy, at that datum is considered to be zero. And so everything else is a change from that. Now, why is that important? Well, you can solve the problem no matter what. Like, if you wherever your datum is, as long as you're consistent, you can solve any problem. But some are going to make it a whole lot easier than others. Like I said, if you're having to do a whole bunch of algebra, it's probably because you're making it really difficult on yourself. Just in all honesty, you're probably making it difficult on yourself. So, looking at this right here, you can see that based on this datum, well, if I'm up here, I've got a positive potential energy. And it's going to be the weight times my distance y. Or if I'm down here, well, I've got a negative potential energy. However, if I've set this as my datum, if that's 0, then I would actually have a potential energy up here of 2 times the weight times distance. So it all is going to depend on where I set my datum. Okay, where you set your datum. And your potential energy at the datum is 0. So in this case, potential energy is positive if you're above the datum and negative if you're below. And you get to set the datum. Similar things happen for our elastic potential energy. Now, usually in this case, your datum is just going to be, the unstretched position. If you choose anything else, you're asking for trouble. For gravity, it's, you got a lot of leeway. This one, just the unstretched position, that is 0. Because there's no energy in that spring. Now, while it initially looks similar, like, oh, well, it's like mass times gravity, it's not the same thing when we go to our energy equation. It's going to be 1/2 ks squared. This is the energy in that spring. And look at this. Do you notice something? It's positive in either direction because it's s squared. It can't be negative. You can't have an imaginary stretch. So no matter what, it's always going to be storing energy. Whether it's being stretched or compressed, it stores energy. Now, as we learn with the principle of work and energy, we're kind of going to apply it here. Before we said, well, if we do work on a system, it's going to change the kinetic energy of the system. Now we're going to say, well, without anything else happening, our total energy in our system is going to be constant, which means that if we take all of our kinetic energy and all of our potential energy, we add it together, well, that's going to be equal to the kinetic energy and potential energy at the end. So that's going to be a constant. This is a really wonderful equation, and it lets you do a whole lot of interesting physics. And just in case you forgot, kinetic energy is just 1/2 mass times velocity squared. Okay, so energy is constant. Spring energy and gravitational potential energy have certain forms. That's all taken into account here. It's both of them. And you get to set the datum. Important things from this lecture. So thank you for listening. I'll see you all next time as we do some examples. Have a wonderful day. Bye-bye.